Assalamu alaikum. My name is Muzaffar and I'm the student of Biomedical Engineering Department Refined National Islamabad. I, along with my group members Moiz Ahmed Bird and Tala Sanullah, created a device that can measure the elbow angle for bowler during bowling. The main purpose behind the creation of this device is to allow the bowler to measure bowling action effectively and efficiently. This project has been supervised by Dr. Muhammad Shafiq. We know that there are very few laboratories in the world that allows the bowler to measure bowling action. Plus, a bowler has to go to a distant place. They have to go to different countries. Plus, a bowler is asked to an unnatural environment. The other problem that is arise is that this is one of the most expensive tests, and the player who belongs to grassroots level, it's difficult for him to access these things. To tackle this problem, we have developed a device that can measure the elbow angle of a bowler. This is the inside of the device that I have weared. Inside you can see that there are two sensors that are based on MEMS technology. There is a microcontroller that is based on the feature of IoT. Due to that, the data is directly sent it to the server and can be received on the mobile phone. As you can see that I am moving my elbow. The data is directly appearing on the mobile phone. You can see it clearly. I will show you the demonstration video in the later part. Following are the components that we have used a pair of MQ650 sensor, we have used 2000 mAh rechargeable battery, we have used Node MCU, jumper wires, and a pair of arm sleeves that I have weared. Now the following are the pinouts for the MQ650. The first two pins are used for the power management. The third pin is the serial clock pin. It basically creates the clock pulse in case of I2C communication. The fourth pin, it's SDA, it is serial data pin. This pin is basically sending data to the Node MCU. And the fifth and sixth pins are the XT and XCL. These are the auxiliary pins, and it's up to us whether we want to use it or not. This pin AD0 is also used for the power management, but it only enables in case of I2C communication. The last pin is interrupt pin. This pin basically tells the microcontroller if there is any data available on MQ650 or not. Now this is the pinout of Node MCU. A Node MCU has 128 KB RAM and 4 MB flash memory. It is a Wi-Fi chip enabled that allows Node MCU to sense the data on the server, and through the server the data can be collected on the mobile phone. It has 17 GPIO pins, general purpose input output pins, but we are only using 4 GPIO pins, GPIO 5 and GPIO 4. They are present on location 20 and location 19. GPIO 5 is the SCL pin and GPIO 4 is the SDA pin. The other two pins that we are using is for power management. The one is 3.3 volt and the other is ground pin. For power backup, we have used 2000 mAh battery. Now these are the schematics. We can see that the power pin from Node MCU directly connects to the VCC of first MPU and AD0 of other MPU. This is the only way Node MCU can differentiate between two sensors. If the power pin is connected directly to the VCC, it means that the sensor is present on location 0x68, and if the power pin is connected directly to the AD0 pin, it means that the sensor is connected on location 0x69. The other pins, that is ground, is common of both with Node MCU, and the SCL pins of both MPU650 connected directly to the SCL pin, which is GPIO 4, and the SDA pins of both MCU connected directly to GPIO 5 pins. That's how the data is being transferring, and through this Wi-Fi chip, the data is sending to the server and collected on our mobile phone. This is the other schematics. Now we'll move towards the video demonstration in which you will see how we are collecting data. Here I will show you the working of our finalized product. I have got a subject named Sufwan Amir who will assist me to show the working of device. At this stage we can see his arm is nearly straight and hardly we are observing any bending rate on our mobile phone. Now to analyze the data at multiple points, the subject is asked to move his forearm up without changing the position of upper arm. We can see that the increased bending angle is clearly visible on mobile application, and we can see that both forearm and upper arm are perpendicular to each other and the angle is nearly touching to the 90 degree. We can see that. Now in the next phase we have to analyze the data by keeping the forearm straight and asking the subject to move his bicep region. Here we can see that when the forearm and the upper arm are getting aligned to each other, the angle is decreasing between them, and we are getting perpendicular to each other, the angle is increasing among them.
At this point, we will ask the subject to move his arm and to show the data on all the regions. We can see that there's hardly any bending at this point. The main purpose of our device was to calculate the bowling angle of the bowler while he's delivering the ball. In this phase, we will show you how we are calculating the bowling angle. When the subject will deliver the ball, there is a button on the top of the mobile application that will be pressed and we can get the finalized angle. Now the subject is ready to deliver the ball, and as he delivered the ball, we have pressed that button and we can see that his finalized angle is 11 degree, which is within the range.
From the working of this device, we can conclude that we have developed a device that is measuring the elbow angle of a bowler effectively and efficiently. We can say that the pair of MQ650 can be used to calculate the joint angle, and the introduction of the feature of IoT in the elbow angle measuring device increases its portability. Plus, it also enables the feature of live measurement techniques. And due to its weightlessness and its appropriate size, this device can be used for other purposes. For example, we can use it as a smart bone measure for measuring the joint angles. That's it from my side. Thank you so much.